Okay, so lecture set 6, the completely randomized block design lecture. This is going to be very similar to what we saw in lecture sets 4 and lecture sets 5. So effectively what we are doing in this lecture set is we are just learning about another method for performing an analysis of variance. So the goal of this lecture set is the same as the goal of lecture set 4. We have a collection of means, so 3 or more population means or 3 or more treatment means, depending on how you want to think about an ANOVA problem. And we want to determine if there is evidence of a difference among the means in our population or among the means in our experiment, again, depending on how you want to think about it. And then following that, we want to perform a multiple comparison if there is evidence of a difference among the means. And then, of course, preceding that, we would just conduct a normality test and a constant variance test, but those will be done in the same way that they were done for the one-way ANOVA, with a very slight twist on the calculation of the residual. Okay, so in this lecture set, I'm going to start off by just explaining why you would want to use a CRBD, so a completely randomized block design, instead of a one-way ANOVA. So basically, we're going to compare and contrast when you would pick between one-way ANOVA and the completely randomized block design. Then what we're going to do is we're going to talk about the structure of the test, the decomposition of the sum of squares for the CRBD versus the one-way ANOVA. And then we'll talk about all the fallout from the test. For the most part, the overlap between this topic and what we saw for one-way ANOVA is very, very similar. So, or what I should say is there's a lot of overlap between the two. So it's a really nice unit because it's all kind of refreshing what we have just learned about in the last couple of weeks, but it's going to help us to understand why we have different types of ANOVA, and it's going to let us think a little bit more deeply about the kind of problems we're approaching and how we can handle issues that come up in the experimental design. So it's really the start of new material, which is great. So all of the review part is kind of over at this point. I suppose it was kind of over with contrast because you hadn't seen this before, but I really like the CRBD unit, and I really like the two-way ANOVA unit that comes up after this. And I think that they're just really interesting studies and how we as statisticians can approach different experimental designs and account for different variables that could come up in those experimental designs. All right, so what is the main difference between one-way ANOVA and completely randomized block design? The main difference is that in a completely randomized block design, we are trying to account for for a variable that we consider to be a confounding variable. So first, when would we apply a CRBD versus a one-way ANOVA? Well, in a one-way ANOVA, we are only interested in studying a difference in means when there is one explanatory factor. That's how we differentiate between that and any other type of ANOVA. So the one-way ANOVA is the simplest type of ANOVA. You have one variable that's essentially splitting your experiment into different groups, or one variable that's being split across different populations, and you want to study the effect of that variable on whatever it is that you're measuring. So you have one response variable and one explanatory variable, essentially. With a completely randomized block design, you have one response variable, so the thing you are measuring. You have one explanatory variable, which is splitting the response variable into different groups. But then you also have a confounding variable, which is something that you want to account for, but not measure directly. And I'll have examples of this coming up in a moment. So the confounding variable, again, is a variable that's present in the experiment. We know that it exists and we want to take it into consideration, but we're not actually interested in studying it directly. So if you think about, for example, the minke whale experiment that we had talked about quite a bit in the last two lecture sets. So in that experiment, the response variable was the length of the minke whale. That's what we were measuring. The explanatory variable was the depth at which they got caught. A confounding variable would be some variable that influences the length, but we don't directly want to account for. Like, I mean, I'm not really an ocean expert, but maybe the quality of food at lower depths is better than the quality of food at higher depths. So that's why those whales are bigger. That might be completely ridiculous, and I apologize if that makes no sense, but we would want to block for quality of food, for example. So something that influences the response, but we don't want to account for directly. All right, so when you have this block variable present and you want to study a difference among a set of population means, that's when we would use a completely randomized block design. So differentiating between it and the one-way ANOVA, or what I mean is picking between it and the one-way ANOVA, just comes down to the presence of this confounding variable. So if the variable is present, we know that it exists, we want to account for it, we would use a CRBD, right? So it's a pretty simple differentiation between one-way and the completely randomized block design. Okay, so what could a blocking variable look like in a more realistic example? So not what I made up for the minke whales. Okay, so here's kind of a classical example of when we might want to block for something. And this comes from an irrigation study, and this tends to be one of the areas where we see these kind of designs or these types of analysis being used. So here we have researchers wish to evaluate the effect of several different fertilization timing schedules on the nitrate nitrogen content found in wheat. Okay, so researchers evaluate fertilization timing schedules on nitrate nitrogen content. Okay, so this is going to be here, the response, and this here is going to be the explanatory variable. Right? So we basically are asking here, is there a difference in average growth or, is there a difference in the average amount of nitrate nitrogen found in wheat across the different levels of this fertilization timing schedule? So the fertilization times are going to have there's going to be 3 or more different timing schedules. Each timing schedule is going to produce wheat that has a certain nitrate nitrogen content, and we want to differentiate between the average amount of this quantity in under each of the different timing schedules. Okay, so to build the experiment, the 6 different treatments are applied to field plots in an irrigated field with a water gradient along one experimental plot area. Okay, so what does that mean? It means that the land is essentially sloped and that water is going to pool at the bottom plot. So the bottom plants are going to get more water than the top plants. And we know that water is going to influence this nitrate nitrogen content. So we want to account for the fact that the bottom plants are going to get, or the wheat in the bottom plots are going to get more water than the wheat at the top plots. So the amount of water here becomes a confounding variable because it influences the response. We know it influences the response, so we don't want to test for it directly, but we want to take it into consideration so that we can perform a fairer test about the difference across the different timing schedules. Okay, so why would we consider this a blocking variable? So as I mentioned before, the plants at the bottom of the gradient are going to get more water than the plants at the top of the gradient. So to control for this, in the experimental design, we go each nitrogen treatment was applied to the field groups in a block of 6 plants. In total, 4 blocks were used, which correspond to different parts of the water gradient. Okay, so we can think of the problem, or we can visualize the problem as follows. So imagine that we have a square grid. Okay. So the grid is going to be 4 by 6. So we'll have 4 rows and we'll have 6 columns. 1, 2, 3, 4, 6. So running down this side is going to be the water gradient. Okay, so we create 4 different rows to account for the gradient. So we'll call those block levels 1 through 4. So we know that block 4 is going to get more water than block 1. And then what we do is we just apply the treatments in each of the categories above. So you might have like T1 here, T2, T3, T4, T5, T6. Okay, and then we can randomize these across the block. So maybe we have T6, T3, T2, T1, T4, T5, something like this. Again, it's randomly applied, so you can kind of just write whatever you want here. So maybe T5, T4, T1, T3, T2, T6 again, whatever. And then T2, T6, T3, T5, T4, T1. I don't know, something like that. Randomly applied. So we know that there's going to be less water here and more water here. Okay. So by blocking, so creating these different rows in the field, we can now get measurements of the averages of the total nitrate concentration across each of the blocks. So by blocking, what we are effectively doing is taking into account the variable that we know is confounding. And by creating these different rows in the experimental design, we're now going to be able to return measurements for each of the blocks separately. In particular, we're going to be able to find average nitrate nitrogen content for each of the blocks. And the reason why we want to do this will become clear once we see the decomposition of the sum of square for the procedure. Because effectively what we're going to do is we're going to take our decomposition of the sum of square, we're going to add another term into that decomposition, which is a term for the block, and we're going to pull the variation from the block out of the total variation. And then this is going to give us the ability to make a more fair comparison about the mean nitrate concentration across each of the treatments. But again, we'll see examples of what this looks like from a theoretical point of view in just a little bit. But the idea itself is pretty neat. So we have the same goal that we had with one-way ANOVA. We have these 6 treatments. Each treatment is going to return an average nitrate nitrogen content. And we want to know, is there a difference in means? Is there a difference among the means of the 6 treatments? We know that there's this confounding variable, so we're going to control for it by essentially allowing it to be similar in each of the blocks, and then we're going to pull the information from the blocks out of our comparison. All right, so let's just write down a few basic points corresponding to this experiment. So what is the response variable? As I said before, so the response variable is the nitrate nitrogen content. So all of our ANOVA experiments have one response. This is consistent. So one-way ANOVA has one response variable. The completely randomized block design has one response variable. And the two-way ANOVA that we're going to talk about in lecture set 7 has one response variable. What is the explanatory variable of interest? So the explanatory variable is the variable that we want to talk about. So this is going to be the fertilization timing schedules. So again, with one-way ANOVA, we would basically be asking, is there evidence that the average nitrate nitrogen content is different across the levels of the fertilization timing schedules? With the completely randomized block design, we're asking the exact same question. So we're asking, is there evidence that the average nitrate nitrogen content is different across the levels of the fertilization timing schedules? However, in the completely randomized block design, while we ask the same question as with one-way ANOVA, we are also going to take into consideration that there's this confounding variable and we're going to control for it. Okay, so the completely randomized block design has two, well, it has one explanatory variable and one block variable. The one-way ANOVA has only the explanatory variable. Okay, so how many levels does the explanatory variable have? 6 levels. There's 6 different fertilization timing schedules. The number of levels just counts the number of different timing schedules. 4, what is the block variable? This is the water gradient. How many levels does the block variable have? In this case, it has 4. So we've created 4 levels for the water gradient. Okay, so both have one response. Both have one explanatory variable. This, and then the CRBD has one block variable. So that's the only difference. We're just accounting for the block. Okay. Any questions so far? Okay, so a completely randomized block design will be typically laid out like what we drew on the previous illustration. So we'll have the treatments lining one column, we'll have the treatments on either the row or the column, and then we'll have the block on the opposite. So if the treatments line the columns, the blocks will line the rows. If the blocks line the columns, the treatment line the row. It's basically just a rectangle where you have a number of entries corresponding to the treatment on either the row or the column or the top or the side, and then the other side is going to be the block. So for every treatment and block, you get one measurement. So this is what the X11 is here. So this is just a measurement of response variable. We let little b count the number of levels of the block. Okay. And then we let little k count, same as it did before, number of levels of treatment. Okay. So X subscript 1, in this case would correspond to treatment 1, block 1. It could also be block 1, treatment 1, again, just depending on if the block is on the row and the treatment is on the column. It just depends on how you want to visualize the data space. So you can see that in the end, you end up with an average for each treatment, which would be the average of the row. So this is the treatment average. And then you end up with a block average as well. Okay, so this is why we're able to end up pulling variation out with the block. So if you recall from our one-way ANOVA discussion, we have the SST, which is split into SS error plus SS treatment. And the SS treatment is just the difference between each treatment mean and the overall mean. Now we have a block mean. So the SS block, which I'll define in a little bit, is just the difference between each block mean and the overall mean. So we're basically just adding the block in, taking block means so that we can then compute a block variance and then just kind of throw it out so that we can compare the error and the treatment directly without having the block absorbed into the error. But I'll come back to talk about that in a little bit. Okay, so every block design is basically just a rectangle where you have treatments and blocks, or blocks and treatments, depending on how you want to look at it. The blocks are going to have B entries and the treatments are going to have K entries. And then we can get block means, treatment means, and overall mean. So the ANOVA model for a completely randomized block design is very similar to what we had for the one-way ANOVA. The only difference is that we now add in an effect for the treatment and for the block. So this is basically like a block mean and a treatment mean. So this is going to be block effect, and this is going to be treatment effect. Now, what does this mean practically? Well, you can see that the error term here is still normally distributed with constant variance. So we have effectively the exact same assumptions on the data that we had in the one-way ANOVA experiment. We're going to assume every single observation is normally distributed in the population of interest, and the true variance of all of the observations is consistent regardless of which treatment block they belong to. So we can say, based off of equation 1, that every observation follows a normal distribution with a mean that corresponds to the block and the treatment that it belongs to and has constant variance. So each observation has a mean that corresponds to the block and treatment level from which it came. So with the one-way ANOVA, we said all of the data are normally distributed. All of the data have the same variance, but the data can belong to their own, the data points can belong to normal distributions with separate means. With the CRBD, we are saying the exact same thing. All of the data are normal. All of the data have constant variance, but the data can belong to normal distributions that have a different mean, where the mean is influenced by both the block and the treatment. Does that make sense? Does anyone have any questions at this point?
Can you say that last part again?
Yeah, so let me just try and draw it because that might help. So I have some room up here. Okay, so with one-way ANOVA, we had xj was distributed normal mu j sigma squared. Okay, so visually, this basically just meant that if we have an axis that looks like this, and say that we had 3 treatment groups, so mu1, mu2, mu3. Each of these treatment groups have the same normal curve sitting on top of them. They just have different means. Okay. And then basically our task with the one-way ANOVA was to determine if these means are statistically different from each other. With the CRBD, we can draw pretty much the exact same thing. Okay, I'm just going to move this over. Right. So if we were to consider kind of like a real line of some sort here, right? And then we were to place a couple of normal curves on top of this. So say here, here, and here. Okay, so then we have the centers shown here like this. The only difference is now there's an effect of the treatment and the block that contribute to the center. So the middle here would be mu plus alpha 1 plus beta 1, for example. And then the mean here could be the mean of mu plus alpha 1 plus beta 2. And then the mean here would be mu plus alpha 1 plus beta 3. And then we would continue to have effectively more normal curves depending on how many treatment levels and how many block levels there are in the experiment. Does that make sense?
Yeah, thank you.
But again, the problem is pretty much the exact same thing, right? It's just we want to know if there's evidence of a difference among the means, but we're only really interested in the treatment effect. So, but we have to take into consideration the block because otherwise we might make a mistake in our conclusion when we're trying to determine if a difference among the treatment means actually exists. Okay, so that part of it, to see why that's true, we're going to consider the decomposition of the sum of squares. Just before I show that, I'll summarize the assumptions here very quickly. So the assumptions are exactly the same as they were for the one-way ANOVA, even though the first one is written a little bit confused, it is a bit confusing to read. So it says, the first one says randomly selected blocks. So the blocks are randomly selected and all create treatments are applied in each block. This is basically just the same thing as saying like, you're not pre-selecting where the blocks go, and you're not determining on your own without any information how the treatments are applied within each of the blocks. So the rationale for this would be you could create an experiment where you block in a certain way to force there to be a significant result. So when we build the blocks, we want to effectively make them, we want them to be kind of like impartially constructed. So we would randomly design the blocks or randomly select the number of blocks for the experiment. So in the previous illustration where we had 4 blocks, you could say that those 4 blocks were randomly picked. Like we could have used 5 blocks or 6 blocks as well, but we randomly selected to use 4, if that makes sense. And then the determination of that number, that's a different discussion. Like you'll be told the number of blocks in all practical situations. But basically, we're assuming that we can say the data are randomly generated within each of the blocks. Question 2, so assumption 2, independent samples. So the treatments are randomly assigned to each observation. So this is the same definition as it was before, like basically just that we can assume that each collection of treatment values are independent of one another. And then number 3 and number 4, normal population and constant variance. Same definitions that we had for the one-way ANOVA. So we assume all of the data is normal. We can check that using residual analysis. And we assume that there's a constant variance across all of the different treatment and block groups. We can do rule of 2. We can compare the range of each of the different combinations, or we can do kind of like a Levene's test across all the different groups. Very similar to what we had in the one-way case. Okay, so if we want to compare the SST one-way or the decomposition of the sum of square of the one-way ANOVA to that of the completely randomized block design, we can see from this decomposition what the block design is actually trying to attempt. So if we consider the one-way ANOVA decomposition. So with one-way ANOVA, we had the sum across all ij, xij minus x bar squared is equal to the sum of each nj x bar j minus x bar squared. This was SSTR. This is SST. And then all we did there was then we added the sum across all j of each nj multiplied by xij minus x bar j squared. And this was our SSE. Okay, so if we pull these terms over, we can see that these two terms here they are equivalent. So we can note SST for CRBD and one-way ANOVA are equivalent. So SST for both designs is just the difference between each observation and the overall mean squared added together. So that is the exact same definition for both types of design. Now, we can also show SSTR for CRBD and one-way ANOVA are equivalent. Now, why is this true? Well, let NJ, so if NJ is the same for all treatment levels, then SSTR becomes the sum of J of little nj multiplied by x bar j minus x bar squared. Okay, so the idea here is basically if nj is exactly the same number for every single treatment level, then we can pull the nj out front of the summation. It's going to be a constant number. And now you can see that the SSTR from the block design and the SSTR from the one-way ANOVA are the exact same measurement. So basically, when we look at the decompositions of the sum of square, you have the exact same SST for the CRBD and for the one-way ANOVA. You have the exact same SSTR for the CRBD and for the one-way ANOVA. So the only thing that is changing is that SSE from one-way ANOVA is now being split into two terms, the SS block and the SSE from the CRBD. Okay, so we have these are equivalent. The SSTRs are equivalent. So SSE from one-way ANOVA is now SSB plus SSE from CRBD. Okay, so what I'm trying to communicate is that you have a one-way ANOVA. The one-way ANOVA says let SST be SSTR plus SSE. Now you have a completely randomized block design. The completely randomized block design says use the exact same SST, use the exact same SSTR, but take the SSE and break it up into two terms, SSB and the new SSE. So what this means from a practical situation is the completely randomized block design is saying account for a confounding variable and then take the information, so the variance from the confounding variable, and pull it out of the error term. And by pulling this information out of the error term, you are effectively decreasing the error. And the reason that you would want to do this is because if you don't account for the block, you're going to have an error term that's inflated. It's going to be too big. So then when you divide the SSTR by the SSE, or when you divide rather the MSTR by the MSE to get your F statistic, the F statistic is going to be smaller than what it should be because you haven't pulled this information out of the error. Okay. Does that make sense? Does anyone have any questions about that? To me, this is like the coolest part of the whole thing, but it's wordy, right? So I admit I'm obviously struggling to convey it really clearly, but hopefully you can kind of get what I'm getting, see what I'm getting at here. Okay, I'm not seeing any questions, but hopefully that's not due to confusion. All right, so now that we have pulled this block term out, we've actually created two F-tests. So we have an F-test for the treatment, and then we have an F-test for the block. The F-test for the block, not that interesting to us because we don't really care about the effect of the confounding variable, but we could say that if the F-test for the block shows a significant result, we might take that as being evidence that that blocking was effective. But really, it's the F-test for the treatment that we focus on. And this is going to work exactly the same way as it did for the one-way ANOVA. We compute an MSTR, we compute our MSE, and we divide them to get an F statistic. And then you'll notice that this F statistic has K minus 1 degree of freedom in the numerator spot. And then it has N minus K minus B plus 1 in the second slot. So this is just like it was before, DF treatment, DF error. So we just have 2 degrees of freedom corresponding to this F value. Right. And then as I said before, we also now we can perform an F-test about the block effect. And usually we use this F-test to determine if blocking was effective. Though technically speaking, it would be the same type of test that we had for the treatment effect. So a test of difference among the means of the blocks across all blocks in the experiment. So the ANOVA table for our CRBD is very similar to the ANOVA table that we had for one-way ANOVA, except that we now have a row corresponding to the block effect. But everything works in the exact same way it did before. The degrees of freedom for treatment, block, and error add to total. The sum of squares for treatment, block, and error add to total. The mean squares are just the sum of square divided by their respective degree of freedom. And then you'll see that the F statistics are just the mean square for the treatment or block divided by MSE. So in all cases, we divide by MSE. But again, because we have the block, the MSE term here is going to be smaller than the MSE from the one-way ANOVA, which should mean that the F statistic we compute here is going to be a better representation of treatment differences if they do exist. Okay, so performing an ANOVA in a completely randomized block design is exactly the same as it was in the one-way case. 6 steps. We state the null and the alternative. We give our significance level, compute the value of the test statistic, and then we use the p-value or critical value approach to make a decision. There are, again, technically 2 different F-tests that we can perform, but most often we're only interested in the F-test about the treatment effect because we want to know if there's a difference in means across the levels of the treatments, whereas we're not as interested in determining if there's a difference in means across the level of the blocks. But we can use the F-test about the blocks to determine if there's evidence that blocking was effective. So if we do reject the null hypothesis for the block effect, that does give us some indication that blocking was useful in the context of this experiment. All right, so we'll start to work through some calculation now. This first calculation is just an illustration of how we would use the sum of square formula. So it says, verify that the block sum of squares is 197. Okay, so we have here SSB is equal to K multiplied by the sum from B equals 1 to little b, from J equals 1 to little b of X bar period J minus X bar dot dot squared. Okay, so this is going to be 6 multiplied by 38.00 minus 42.07 squared plus 45.89 minus 42.07 squared plus 43.11 minus 42.07 squared plus 41.29 minus 42.07 squared. Okay, and then this should give us 197.00. But again, this is just an illustration of how the formula works. The treatment formula would work in the exact same way. And then I would recommend, if you're in a situation where you need to compute these things, which I think you will have to do on assignment 4, if I recall the structure of the assignment correctly, you'll also have to compute an SST term, which is just going to be the difference between each observation and the total squared added together. You could compute SSE if you wanted to, but typically computing the error term is more difficult. So it's easiest to do treat SSB, SSTR, and the SS total. All right. Okay, so there's only 5 minutes left. Let's just look through an illustration of how the block, of how the CRB, one-way ANOVA for the CRBD, sorry, of how an ANOVA would work for a CRBD. So going back to the original example, we want to know if there's evidence of a difference in average nitrate nitrogen content across the 6 fertilization timing schedules. So we've performed a completely randomized block design. We have computed SSTR, SSB, SS error, SS total, and all the corresponding values in the ANOVA table. Our null hypothesis is going to be alpha 1 is equal to alpha 2 is equal to alpha 3 is equal to alpha 4 is equal to alpha 5 is equal to alpha 6. So basically, the null hypothesis is that there is no treatment effect, versus the alternative that not all treatment means are equal, which is the same thing as saying there is a treatment effect. We tested the 5% significance level, and then we calculate an F statistic or a test statistic for the treatment effect, which you can see here is 5.59, and that's found just by taking 40.26 and divided by 7.20. So all the values in this table should be easy to compute. And then you can see that the p-value, the exact p-value for this test would be 0.04. Okay, so on step 4, the p-value is 0.004. The critical value is going to be an F value on 5, 15, and 0.05. So notice that the critical value takes treatment, the DF for the treatment, the DF for the error, and then it takes the significance level. So this would just be found using the F table, the same way that we have seen before. And then on step 5, we can say since the p-value is less than alpha, we can reject H0. Alternatively, since the test statistic or the F stat is greater than F515, then the critical value we can reject. And then we can say that there's significant evidence of a difference in average nitrate nitrogen content found across the 6 fertilization timing schedules. So this is all just review of what we saw before. The next exercise that I want to show you is an example of performing the F-test about the block. So I'll start, because I only have a few minutes left, and I'll just get it started, but we'll have to finish this up on Wednesday. So as I mentioned before, we can conduct an F-test about a difference in the block means. Again, we're not overly interested in this type of test because we really want to know if there's evidence of a difference across the treatment effect, but we can use this test to determine if there's evidence that blocking was efficient or just if there was a block effect at all. So you can imagine that if you do not reject the null hypothesis in the test about the blocks, you're basically just saying like there's no evidence that blocking, there's no evidence that the means are different across the blocks, which would imply that there's no evidence to suggest that blocking was efficient or is effective. Whereas if you do reject the null hypothesis for the block effect, that would give evidence of a difference in means across the different levels of the blocks, which would mean that there was a reason to block because there is this difference in the means. So performing this test would be very similar to what we saw for the treatment. So we'll have beta 1 equals beta 2 equals beta 3 equals beta 4 versus the alternative, not all block means are equal. And then on step 2, we'll have our significance level. And then on step 3, we'll have F for the block is going to be MSB divided by MSE, which from our ANOVA table will be 65.67 divided by 7.20, which is 9.120833. Right, so again, very similar to what we saw before. And then on step 4, we can take the p-value or the critical value approach. And this is where I'll pick up on Wednesday, is working through the steps of the test so that you can have another illustration of how this works as well. Okay, so that's basically your introduction to a completely randomized block design. From a statistical point of view, the way that the design operates, or the way that the F-tests operate, is exactly the same as they did for one-way ANOVA. But from a composition point of view, what the block design does is it accounts for a confounding variable by pulling variation from the error out, or pulling information from the error out, so that we can make a more fair comparison about the treatment effect on the means of the response variable. Okay, so as always, if you guys have any questions, please let me know. And on Wednesday, we'll just pick up where we left off and keep talking about block designs. And then on Friday, maybe we'll get to do a little bit of two-way ANOVA stuff before we break for the reading week. So have a good couple of days, and I will talk to you on Wednesday afternoon.